In this video, we're going to look at related rates. I'm making this video for my students who are reviewing for the AP test, and they have asked for a related rate review. So this is what you guys asked for, and I don't want you to be like this guy right here who looks at related rates and just has no idea what to do. Don't let this be you. So in this video, we're going to spend time conquering related rates. So before we can talk about related rates, we have to go back and figure out what are related rates. And related rates are simply application problems, meaning word problems, that involve using the chain rule or implicit differentiation. So let's go back and let's talk about the chain rule. The chain rule is used to find the derivative of a composition or a composite function such as f of g of x. And you can see in this case that f is the outside function and g is the inside function. So let's look at two examples of using the chain rule and using some implicit differentiation. I have two expressions here, or two equations. The first one, I have an explicit relationship, or an explicit function in this case, where y is by itself, so that makes that explicit, and that's easy to take the derivative of. And on the right-hand side, I have the equation of a circle, x squared plus y squared is equal to 3. And that is an implicit relationship because we have our variables are not isolated. I could isolate either x or y, but that could possibly make the problem more difficult. In the example on the left, when I take the derivative, we are literally doing an operation. We are taking the derivative of each term, the derivative of y, the derivative of 3x squared, and the derivative of 1. And notice, in this case, I'm taking the derivative with respect to x. Now, first thing I notice is that I have variable disagreement between the variable that I'm taking the derivative of and the variable I'm taking derivative with respect to. Variable disagreement. In the second, on the right-hand side, the first term, when I take the derivative, I have variable agreement, and in the third term, I'm just simply taking the derivative of a constant. So on the left-hand side, when I take the derivative of y with respect to x, technically I get 1, but I don't need the 1, times dy dx. So I'm really doing the chain rule there. I'm really doing some implicit differentiation because the derivative of y is 1, and the inside function is the y, and the derivative of the y is dy dx. So there really is implicit differentiation there, even though at this point in calculus we really didn't need to talk about the implicit differentiation. On the right-hand side, when you take the derivative of 3x squared with respect to x, you get 6x by the power rule. And then by the chain rule, you get dx dx, which is really just undoes each other and is 1, and the derivative of that constant is 0. So the derivative of 3x squared plus 1, the derivative of 3x squared plus 1 is 6x. And we really didn't need to do all that implicit and chain rule stuff. We could have gone directly from here to here. But I wanted you to see that the chain rule was being applied, even though it was not quite as apparent. In the second example, as I said, I have the equation of a circle, and I'm going to take the derivative with respect to x of both sides, all terms. And so for the first term, we have variable agreement. For the second term, we have variable disagreement, and on the right-hand side, we're simply taking the derivative of a constant. Because we have variable agreement in the first term, there's my little smiley face, we take the derivative as normal, and we get, using the power rule, the derivative of x squared is 2x. Very simple, variable agreement. In the second term, I want you to really look and see where the chain rule is coming in here. I decided to take y, and oftentimes, instead of y equal to something, we could replace y with f of x, and that's exactly what I did in this case. So I replaced y with f of x, and it's raised to the second power. Now you can really clearly see that we need a chain rule because there's an inside function and an outside function. Using the power rule, I get the 2, decrease the power by 1, there's the chain rule, leave the inside function alone, multiply by the derivative of the inside, and there's that f prime of x. There's where that dy dx comes from. So the derivative on both sides gives me 2x. I'm taking the f of x back out and putting the y back in its place, and in place of f prime of x, I'm substituting dy dx, so you can actually see that that chain rule is required for that particular term. So one of the keys to identifying a related rate and implicit differentiation is looking for that variable disagreement. If you see the variable disagreement, it definitely requires the chain rule, and you have to leave behind that dy dx or that dy dt or dx dt, depending on the variable you're differentiating with respect to. So let's get back to what we really are here for. Let's talk about related rates. So to win a related rate problem, to conquer it, to defeat it, the first thing you have to do is to recognize a related rate problem using your math eyes. You have to be able to see it. You have to know what are the key words that are telling me that I have now entered a related rate problem, and we're going to talk about that in the video. Second, you have to read with your pencil. That means you have to record the important information that will allow you to solve the problem. This allows you to create what I call a box of knowledge, meaning everything that's important I write down on my paper in a little box that helps me to figure out if I need to know something, I look in my box of knowledge. We'll talk a little bit more about that later. Next, you need an equation that relates your variables. So you begin with related variables, and when you take the derivative, you end up with related rates. In an AP problem, this equation is often given, but sometimes you have to write your own based upon the context of the problem. And then finally, to complete the related rate problem, you take the derivative of both sides of your equation with respect to the variable indicated in the context of the problem. It could be with respect to x, with respect to t, which will involve using the chain rule when there's variable disagreement. Remember, we talked about that, the yes, no, the xy, the xt. So now let's get back into the related rates and let's see some related rates in action. I've taken some problems from AP Classroom as well as some real live AP problems to try to help you to be able to use your math eyes and your box of knowledge and your skills to solve a related rate problem. So what I would encourage you to do right now is to stop the video to see if you can solve the related rate problem below, and then resume the video to check yourself. So I'll give you a second to stop the video, and then I'll resume and then unpack this particular related rate. So in this related rate problem, I have the radius of a sphere is increasing at a constant rate of 0.04 centimeters per second. The volume of a sphere with radius r is v equal 4/3 pi r cubed. At the time when the volume and the radius of the sphere are increasing at the same numerical rate, what is the radius? So let's talk about first questions I would ask you would be, what did you read? And more importantly, what did you write? So when I read this problem, the first thing that triggers me is I see the word radius, and they come back over here and they talk about the radius rate. And they tell me that the radius rate is 0.04. So the first thing I would write on my paper is, translating that out of words into symbols, dr dt is 0.04 centimeters per second. The next thing that I notice that they have given me is the formula for the volume of a sphere, so I would record that formula on my paper. And then they tell me exactly what to do. When the volume and radius are increasing at the same rate. So volume rate equals radius rate. They want me to find the radius. So I'm going to get rid of the words and I'm going to write down what I just read. Find r, that's what they told me to find. And they told me to find r when the volume rate, dv dt, is equal to the radius rate, dr dt. So I begin with my volume formula, because if you're still wondering, well, I still don't know what to do, this is what I'm going to do. I'm going to find dv dt, and I'm going to set it equal to dr dt. So right here in this step, to find the derivative of v is dv dt, and on the right-hand side, I'm going to find the derivative using the power rule. So when I find the derivative using the power rule, I will get 4 pi r squared, and then there's that chain rule, dr dt, the implicit differentiation. That's dv dt, and I'm setting it equal to dr dt, which is exactly what they told me to do. You can't make this stuff up. You just do what the problem tells you to do. Now I'm solving for r, and I notice that I have a dr dt on both sides, so I can divide that out, and that leaves me with a 1 on the right-hand side. I'm solving for r, so I divide both sides by 4 pi and take the square root. And so when the radius is 1 over 2 square root of pi centimeters, the volume rate and the radius rate equal each other, which is exactly what they asked me to find. Let's go on to the second problem, and again, I would encourage you to stop the video, see if you can solve it, and then resume the video to check yourself. Okay, let's take a look at this problem. The radius of a sphere is the same setup. The radius of a sphere is increasing at a constant rate of 0.04 centimeters per second. They give me the volume formula again, but this time they ask me a different question. This time, they want the time. At what time? I'm sorry, I misread that. That's not correct. At the time when the volume of the sphere is 36 pi cubic centimeters, what is the rate of increase of area? So there it is, keywords, area rate. What is area rate of a cross-section through the center of the sphere? Now that cross-section means simply I'm going to slice this circle. Let's see if I can trace that through the center and basically get circular, and the area of a circle is pi r squared. So let's see what I have in my box of knowledge. I recorded the formula for the volume of a sphere again. I recorded that they wanted me to find the area rate, dA dt, when the volume is equal to 36 pi, and they also told me again that dr dt is 0.04 centimeters per second. So I'm going to begin by doing exactly what they said. Set volume equal to 36 pi. So I don't have to make this up. They told me to do this. Do what the problem tells you to do. So I'm going to set the volume equal to 36 pi, and that's going to allow me to find a value of r. The pi's divide out on both sides. Then I can multiply both sides by 3/4 to get r by itself. Take the cube root of both sides, and I found that r is equal to 3. That's phase 1. Second part, now I'm going to get into the related rate part, or the implicit differentiation. They said that we're finding the area of a circle, and the area of, or the rate of change of the area of a circle. The area of a circle is pi r squared. I'm going to take the derivative on both sides with respect to time, so the derivative of a would be dA dt, and on the right-hand side, by the power rule, the derivative of pi r squared is 2 pi r, chain rule, dr dt. Substitute the 3 that I found over here, because I am going to need that radius. Substitute the 0.04 that they told me about right here, and that will give me the rate of change of the area. And since it's rate of change of area is measured in square centimeters, so we have a rate of centimeters square per second. All right, now let's move into a real live AP problem. Once again, stop the video, see if you can solve this problem, and then resume it to check yourself. So this is problem number 4 from the 2019, one of the free response question. It's a no calculator question, not that that really is our big deal here. So let's see what this problem has in store for us. A cylindrical barrel with a diameter of 2 feet contains collected rainwater as shown in the figure above. My figure's over here to the right. The water drains out through a valve that's not shown at the bottom of the barrel. The rate of change of height of the water in the barrel with respect to time is modeled by, this differential equation, dH dt equal to negative 1/10 square root of h, where h is measured in feet and t is measured in seconds. The volume of a cylinder with radius r and height h is v equal pi r square. So let's see what I did when I was reading with my pencil. The first thing that I noticed is that the diameter of the barrel is 2 feet, telling me that the radius of the barrel is 1 foot. Now the nice thing about a cylinder is that the radius never changes. In a cone, the radius does change, but the radius here is always going to be 1 foot, which makes that a constant, which means we can substitute it from the very, very beginning of our work, and we should always substitute constants at the beginning of our work. The next thing that I noticed is that I have a differential equation of dH dt, and I wrote it without a square root. I wrote it with h to a 1/2 power. And I have the formula for the volume of a cylinder, which is pi r square h. All right, so there's my box of knowledge and the information that they've provided for me. Let's find out what we're doing next. So the next thing that we're going to do, let's get this out of our way. So the next thing that we're going to do, find the rate of change of volume. So volume rate is dV dt with respect to time when the height is 4. So again, reading with my pencil tells me that I am to find dV dt, just like I said, when h is 4 feet. So this is what's telling me exactly what to do. I need to take the derivative of volume, and I need to take the derivative of volume with respect to time. However, it's really important to remember that we said that r is a constant, r is 1, and it can go in from the very beginning, not after differentiation. If we were to take the derivative of this formula as written, we would have the product rule, we would have a dr dt, we would have a dH dt, and unless you realize that dr dt is equal to 0, you have a real problem on your hands that you're going to get stuck in. So I begin with the formula given to me for volume, pi r square h. As I said, we're going to substitute the 1 from the very beginning, which gives us a simple formula for volume to be pi h. So now really my formula is V equal, never mind, V equal to pi h. So I'm going to take the derivative on both sides and using implicit differentiation and the chain rule. So the derivative of V is simply dV dt. The derivative of the pi h is pi dH dt, there's my chain rule, and I'm evaluating that at 4. Then I'm going to substitute, remember we know back up earlier in the problem, let me clear my board here a little bit, we know that dH dt is equal to negative 1/10 h to the 1/2 power. So I'm going to substitute that in place of dH dt. That's where that's coming from. And I'm evaluating at 4, so I substitute 4 in place of h, and I get negative pi over 5 cubic feet per second. Now there's another implicit part of this problem. In part B, it tells us when the height of the water is 3 feet, is the rate of change of height, there it is, height rate, is dH dt increasing or decreasing? So I recorded on my paper, when dH dt is 3, got it from there, is dH dt, got it from here, increasing or decreasing? Well, to know if dH dt is increasing or decreasing, we need to know the derivative of dH dt, which is technically, or not technically, is the second derivative of h. So I have to take the derivative of dH dt implicitly in order to determine whether I'm going to output a positive or a negative. So I'm going to begin with dH dt. That was the formula that they gave me. I'm going to take the derivative on both sides. So the derivative on the left side will simply give me the second derivative, d squared h over dt squared. On the right-hand side, I'm using the power rule, so multiply and decrease the power by 1. There's the chain rule, dh dt, leave that behind. Then I can move the h to the negative 1/2 power to the denominator and make that square root of h. I can substitute, I know what dh dt is, remember from the given, so I'm going to substitute that in place of dh dt. And then when I simplify, the square root of h's divide out, and a negative times a negative is a positive, and that's really all I needed to know. So I can now say that because the second derivative is positive, the rate of change of height, dh dt, is increasing when the height of the water is 3. Let's move on to the 2018 question number 4. Stop the video to see if you can solve the problem, and then resume the video to check yourself. And in this one, we're going to do part D only. So 4D, let's see if I can get all of that in the window for you to see. Hope I did that for the last problem. All right, now that you're back, we're going to resume, or we're going to take a look at this problem. The height of a tree at a time t is given by a twice differentiable function. Oftentimes I get a question from students, what is a twice differentiable function? That just means that h has a first derivative, h prime, and that h has a second derivative, h double prime. That also tells you since h has a first derivative, h is continuous, and since h has a second derivative, h prime is also continuous. H of t is measured in meters and t is measured in years. Selected values of the height, or h of t, are given in the table above. Let's look at letter D. What do they want us to do? The height of the tree in meters can also be modeled by the function g. So now they've told us to kind of ignore the table for now, and they have a new function which also models the height of the tree, except for this time now it's called g instead of h, where x is the diameter of the base of the tree in meters. When the tree is 50 meters tall, remember the height of the tree is g. When g is 50 meters, the diameter of the base of the tree is increasing. Now remember, diameter was measured in x, so the diameter x is increasing at a rate, meaning dx dt is 0.03 meters per year. According to this model, what is the rate of change of height? So we want the height rate, which in this case, remember, height is g, so we want dg dt. So hopefully in your box of knowledge, you wrote down, we know that g is 50, we know that dx dt is 0.03 meters per year, and our job is to find dg dt when g is equal to 50. So to find dg dt, we have to begin with the function g. So let's take a look at my work. So the derivative on the left-hand side is just dg dt. That's extremely easy. And on the right-hand side, I'm going to need the quotient rule. Down d up minus up d down over down down. But when I take the derivative of an x term, because we're taking the derivative with respect to time, I get a dx dt here, and I get a dx dt here in my quotient rule. Notice that to evaluate this, we are going to need the value of x, and we're told the value of dx dt. So we're good and we're good, but we do not know the value of x. We know the value of g. We need a value of x. But that's okay because our equation connects g and x. So I'm going to substitute 50 in place of g, which I did right here. And I'm going to cross multiply to solve for x. So cross multiply, and x turns out to be 1. So now I can substitute the 1 in place of the x and the 0.03 in place of dx dt. And for the AP test, I can leave my answer just like this. I do not have to multiply it out. I don't have to simplify it out. Even if I have a calculator, I don't have to do that, because if I type one wrong number, then I'm going to lose the answer point. Let's look at one more question, one more related rate question. And if you're in my class, we're going to do some practice problems in class now that you've had a chance to review this through the video. Once again, I would encourage you to stop the video to see if you can solve the problem, and then resume the video to check yourself. So in this problem, we are looking at parts C and D. And we have a table of values given to us. Let me bring that down a little bit so we can see hopefully both questions and at the same time. Yeah, that kind of sort of does it. Okay, a tank has a height of 10 feet. The area of the horizontal cross-section of the tank at height h feet is given by the function a, where a of h is measured in square feet. The function a is continuous and decreases as h increases. Selected values of a of h, area, are given in the table above. So h is feet, a of h is square feet. When we get to part C, the area in square feet of the horizontal cross-section at height h feet is modeled by the function given by. So now they're kind of moving us away from the table, and they're giving us a function, kind of like that last problem, that produces the area in square feet for us instead of looking at the table. Based on this model, find the volume of the tank. Indicate units of measure. We're not going to do that problem. We're going to jump to letter D because we need this. The reason that C is here is because we need it to do D. D is our actual related rate problem. So in D, water is pumped into the tank. When the height of the water is 5 feet, the height is increasing at a rate, so there it is, height rate, dH dt, 0.26 foot per minute. Using the model from part C, and that's why part C is here, find the rate at which the volume, there it is, volume rate, find dV dt, is changing with respect to time when the height of the water is 5 feet. Indicate units of measure. So just a few reminders here. Don't quit. Make sure you persevere. Let's look at my box of knowledge and compare it with your box of knowledge. I said when the height is 5 feet, dH dt is 0.26 feet. Find dV dt. Now, there's no V in this problem, and nowhere do they actually tell us a volume formula. So we got to think about this. We need a volume formula so we can take the derivative of the volume. Well, in part C, notice that this model is not for volume. This model is for area and is measured in square feet. But we know enough about calculus to know if we were to integrate the area, and I'm just going to use an A right now. I know this is not A, it's at f of h. But if we were to integrate area with respect, I'm sorry how sloppy this is, area with respect to time, that would take us back to volume. So that's what I'm going to do. I'm not literally going to integrate, but I'm going to try to help you understand where we're getting the volume rate from, because I need dV dt. So let me unpack what I just said. In this problem, to find volume, we would integrate the function in letter C. We would integrate f from 0 to h, and that would give us the volume. When we take the derivative by the fundamental theorem of calculus part 2, that would give us, on the left-hand side, the derivative of v is dV dt. The derivative on the right is f of h times the derivative of the new function. So we take out the x, put in the h, multiply by the derivative of h, which is dh dt. And that's where we get our volume derivative from, our volume rate. This one's a little bit more tricky because it just didn't use that v, and so you had to think about, how do I come up with a v? Then I'm going to substitute f of h, which they gave me in part C to be this formula right here, dh dt. And then I'm going to substitute the numbers that they gave me, and I did not evaluate that out on my calculator, and that would be cubic feet per minute. So that's it for now for this particular related rate video. I hope that helps you, moves you forward a little bit. And before I close, I would just say, pay attention to these two signs. Don't quit and persevere. You can do related rate problems. Every time you do one, determine that you're going to do better and do more on this one than you did on the last one. And if you're in my class, we'll be practicing these for the AP test.